Okay, 1 minute past 4. Hello, everybody, and welcome to today's ENLA seminar. My name is Jörg Diesen, and hello from Berlin. Good afternoon, good morning, or good evening, wherever you are. It's a great pleasure for me to introduce today's speaker, Erin Carson, from the Faculty of Mathematics and Physics of Charles University in Prague. Erin obtained her PhD in 2015 with a thesis on communication avoiding Krylov subspace methods in Berkeley, which was supervised by Jim Demmel and Armando Fox. In addition to the communication avoiding techniques, such as S-step Lanczos and CG, for example, the main focus of Erin's work is the rigorous finite precision analysis of iterative solvers. She's also working on multiple or mixed precision numerical linear algebra. And in this area, one of her most frequent co-authors is Nick Hayem. Erin is currently the principal investigator of the project Scalable and Accurate Numerical Linear Algebra for Next Generation Hardware, which is sponsored by the Primus Research Program of Charles University. And let me mention that on her website, there's an announcement of an open postdoc position in the project with the deadline for applications at the end of this month. So Erin has an impressive list of invited presentations, and we are happy that she accepted our invitation to speak in the ENLA seminar today. And as you can already see, she will talk about what do we know about block Gram-Schmidt. Before handing over to Erin, I would like to point out a few things. As usual, all participants are encouraged to ask questions in the Zoom or YouTube Q&A, and these will be handled by Daniel Kressner for Zoom and Bart van der Eycken for YouTube today. The Zoom format is a meeting, and hence we will be able to unmute participants so that they can ask their questions directly. And then please note that all the questions and webcams, if activated, will be recorded also. So finally, for today, we will keep the Zoom meeting running for some time after the recording of the meeting has stopped, so that everybody can engage in an open discussion afterwards. So you can already start thinking about things you would like to share with others, for example, announcements of meetings or other things that you find of interest for the NLA community. Okay, good. So now I hand over to Erin, and please go ahead with what do we know about block Gram-Schmidt?
Okay, thank you very much for the introduction, and I want to say thank you to the organizers for the invitation and the opportunity to speak in this seminar. It's really a great honor for me. And so I am relatively new to this topic, and I'm sure some of you are wondering, why I chose to talk about this today. And I'm also sure that there are many people in the audience who have been thinking about these things much longer than I have. But I will try and do it justice, and let me give you a little bit of background of how I got here. So our work on this started as a project with my now former postdoc, Catherine Lund, and we wanted to look into proving something about the backward stability of S-step or communication avoiding GMRES methods. And so the first thing you look at there is the stability of the block orthogonalization scheme. And we started to realize that, okay, there's a huge landscape of potential different combinations of schemes for orthogonalizing between blocks and orthogonalizing within a block. And so we started to try and collect all known results on the stability of block Gram-Schmidt orthogonalization variants. And what we realized is that while a lot of work has been done in this area, there are still a ton of open questions. And it seems like some of the results are not that widely known. Right, so if you've ever thought about using a block orthogonalization scheme, in particular within a block Krylov subspace method, I hope this talk will be useful to you and will shed some light on what kind of numerical behavior you might expect. Okay, and so before I start, I want to thank my collaborators, in particular Catherine Lund, who really took the initiative on this work and put all these results together and proved some interesting new results that I'll talk about. And along the way, we convinced Miro to work with us, who is our local Gram-Schmidt expert, and also Steve, who's the main force behind these cool new low synchronization variants that I'll talk about. Okay, so we'll start with the basics. And so we have a set of linearly independent vectors x, and we want a set of orthogonal vectors q that span the same space. And so there are many different ways of doing that. Okay, you can do householder transformations or Gibbons rotations or Koleski QR, but the method I'll focus on today is the Gram-Schmidt process. And so here's a small depiction of how this works for two vectors, and if you had more than two vectors, you can just continue the process in the same way. Okay, and so if we want the vectors to be orthonormal, we'll just divide each vector by its norm. And what this means is that each x can be written as a linear combination of q1 through qk. Right, that means I can write x is equal to qr, where the columns of r give me the linear combinations of the q's I take to get the x's. And so typically we require that the diagonal entries are positive, which is done via normalization here, and this gives us a unique QR factorization. Okay, so orthogonalization of vectors has a huge number of applications. I'm sure I don't need to convince you of that, so very useful for solving least squares problems. It's also used within Krylov subspace methods to build up an orthogonal basis for a Krylov subspace. And our main focus here today will be what happens in finite precision. All right, so when I perform a floating point operation, I might make a tiny rounding error, and those tiny errors can accumulate or be amplified over the course of a computation. And so that means that the inexact q, this q bar here, right, no longer has exactly orthonormal columns. Right, and also q times r is no longer exactly equal to x. I no longer have an exact QR factorization. And we care about this because it can affect applications downstream. The extent to which really depends on the application. Right? For example, in eigenvalue computation, this is particularly sensitive to having a good orthogonalization. And so we have a number of different ways that we can measure the error in a finite precision orthogonalization process. Right? So the first is the loss of orthogonality, which says how far q is from having orthonormal columns. Right. The second is the relative residual norm, which says how close q times r is to x. And the third is what we call the relative Koleski residual norm, which bounds how close r transpose r is to x transpose x. And so the relative residuals will be order epsilon. It's not too difficult to get a good relative residual, but it's harder to get a nice bound on loss of orthogonality. And that's generally the most difficult for an algorithm. And so we'll focus on that as kind of our main indicator of stability in this talk. Okay, and so if you look at any textbook, right, these are the textbook versions of Gram-Schmidt. So we have what's called classical Gram-Schmidt and modified Gram-Schmidt, and I'll use these abbreviations CGS and MGS. All right, the implementations here look almost identical. The only difference is whether I'm projecting onto my original vector x or whether I'm projecting onto the intermediate already partially orthogonalized vector w. And so that tiny change to the algorithm has really significant implications, right? So the first, there's a formula by which we're computing the entries of R. The second is how the next orthogonal vector is computed, right? So if I rearrange the loops of those algorithms a bit, you can see that in CGS, I'm actually using this projector, right, to get my next Q or W vector, right? Whereas in the MGS case, this projection is split up into pieces, right? And that'll have big implications for stability. So if we look at the bound of loss of orthogonality, right, in the case of MGS, we expect this to be bounded by order epsilon, and this kappa I'll use, this is the condition number of X. Right, and so whereas in the CGS case, the only bound that we have proven is very bad, right? This is a terrible bound here, right? But it does hold, right? And these bounds hold under some constraint on the condition number of my matrix. Right, and so the trade-off there is that MGS is more expensive than CGS, right? If I just look at the number of messages or synchronizations in the parallel versions of these algorithms, right? So MGS has order K in loop K, whereas CGS just has a constant number. Right, so there's generally a trade-off between how good our computation is and how fast our computation is. All right, I want to take a brief moment. This is obligatory for a talk on Gram-Schmidt, just to talk about the history, because this is amusing to me. All right, and so this information pictures were taken from this very nice article of Leon Bjorkengander. All right, and so what we call classical Gram-Schmidt was popularized in this paper by Schmidt in 1907. And in that paper, he has a footnote that says, okay, this algorithm here is essentially equivalent to what Gram did earlier in 1883. And it turns out what's in Gram's paper is actually equivalent to modified Gram-Schmidt. All right, so it's amusing to me that what we call classical actually came pretty far after what we call modified. And then in 1935, Wong stuck the names Gram and Schmidt together, and it's stuck ever since, right? And so it actually turns out that Laplace did this, even before Gram, right? And people were using something equivalent to modified Gram-Schmidt. Okay, so the idea comes pretty naturally that instead of just doing Gram-Schmidt one vector at a time, let's do it on a block of vectors at a time. And there are various reasons why you might want to do that. So one is that I want to make use of BLAS 3 operations, right? So instead of BLAS 2, and that'll get me better performance. Another reason is I might be running a block Krylov subspace method, which requires you to use a block orthogonalization scheme. And you might do that not only for performance reasons, but also numerical reasons, right? I might get better convergence on problems with clustered eigenvalues, for instance, right? Or in your application, you might have multiple right-hand sides that you can solve simultaneously, and so it makes natural sense to use a block method in that case. And there are also variants like SSEP or communication avoiding Krylov subspace methods, which reduce data movement by computing with blocks of basis vectors at a time. And so in this talk, my big matrix, right, will always be M by N, right? And there will be P blocks, each of size S, right? And I'm going to assume that P divides N to make things simple. And I'm also going to assume that the blocks have a uniform size, right? They're all the same. All right, so what do we need to define a block Gram-Schmidt variant? Okay, so we need two pieces, right? And we will sometimes refer to these as the skeleton and the muscle, which is an analogy that comes that Mark Homan used in his 2010 PhD thesis. And this is the least gross picture I could find of a muscle and skeleton on the internet. But the skeleton is what we would call the interblock orthogonalization scheme. Right? So what we use to orthogonalize between blocks. And here we'll restrict ourselves to the case where that's a block Gram-Schmidt algorithm. Okay, then the muscle, or what's doing the local work, right, is what we use as the intrablock orthogonalization scheme, right? So what we're using to orthogonalize vectors within a block. Right? And people also call this local QR or panel factorization in the literature. And so here, this will be a non-block algorithm, and it doesn't necessarily have to be Gram-Schmidt based. It could be householder QR or Gillespie QR or whatever. And I'm going to frequently refer to that as the intra-ortho, right? So it's doing the intra-block orthogonalization. And just as an example, so if we want to use block modified Gram-Schmidt, right, for orthogonalizing between blocks and householder QR within the blocks, I would denote this using this composition notation, right, which we'll use throughout the talk, right? So this is using block modified Gram-Schmidt and then householder QR within blocks. Okay, and I'll also use a naming system that might differ from what you have seen in the literature, right? Because there's a lot of inconsistencies actually. So just for example, the suffix "to" is used in different places by different people to mean, a reorthogonalized variant, a version that uses BLAS 2, or sometimes just a second version of the algorithm. So to try and make things consistent, we'll adopt our own naming scheme, but make it clear when things are called other things. All right, so for reorthogonalization, just example. So the plus will mean the algorithm is literally just run twice. Like I run CGS and then I run it again on the output. The I plus will mean inner reorthogonalization, meaning the inner loop is performed twice in a row for each iteration. And the S plus will mean selective reorthogonalization, right, where there's some condition by which I'm deciding whether or not to rerun the loop iteration, and there are various criteria for that defined in the literature. Okay, and second, I need to define some notation for the block matrices. So whenever I use script or calligraphic letters, these curly guys, these will refer to the big block matrix. And then the regular X, Q, and R will be the blocks themselves, right? And so in stating bounds on error, inexact computed quantities will be denoted with a bar. Right, and so to restate, I'm going to have an M by N block matrix, and the individual blocks will be of size M by S, and there will be P of them, right? And these are alphabetically ordered, so it's hopefully easy to remember. Okay, and so I'll always take QR factors here to be economic QR factors, meaning that Q is M by N instead of M by M, right? And R is square, right? And so Q and R will have the same block structure that X does, and I'll often use this MATLAB style indexing when I want to take the first J blocks of Q or the first J blocks of column K in my block R. And I'll also note here that we're going to focus on scenarios where the block vectors may not all be available at once, right? As is the case in block Krylov methods. Okay, and so block Gram-Schmidt algorithms have been around a long time, and I cannot hope to point out every piece of work that has ever used block Gram-Schmidt, but I will just name a few that fit on one slide in order to make a point. Okay, so in 1984, Boley and Golub used a reorthogonalized block modified Gram-Schmidt with reorthogonalized modified Gram-Schmidt, right? And they have this interesting quote from the paper, which says, okay, since I got this block Z from a block Gram-Schmidt orthogonalization against the previous blocks, what's the harm in continuing to use Gram-Schmidt to orthogonalize within the block? And I say that's interesting because it's somewhat misleading if it's taken out of context, right? It's true for their particular case when we're talking about the case where they use both modified Gram-Schmidt based muscle and skeleton with reorthogonalization. That's fine, but this is not necessarily a true statement for any variant of block Gram-Schmidt. Okay, there's also work by Simoncini and Galopoulos that uses a block modified Gram-Schmidt with modified Gram-Schmidt inside the blocks. And this was also used in the PhD thesis of Vital. And this is a very common choice that people use. And then a lot of time in the literature, it isn't really clearly specified what is used as the intra-ortho routine. It's just specified as AQR factorization. And so one could just, we might have interpret these to mean householder QR, but it's not really clear, right? And in some, it would in some ways, it might lead you to think that, okay, maybe it doesn't really matter what I use as the QR factorization, right? Maybe as it's suggested in this earlier quote, I'm already doing block Gram-Schmidt, so why not just use some Gram-Schmidt for the local QR factorization too? And so we asked, does it really matter what you use? And so remember that for modified Gram-Schmidt, the loss of orthogonality is bounded by order epsilon kappa x. Right? And so what is the bound on the loss of orthogonality if I use block modified Gram-Schmidt with modified Gram-Schmidt inside? Right, so I'll give you a few seconds to make a guess in your heads. Okay, your time's up. All right, the answer is that for block modified Gram-Schmidt with modified Gram-Schmidt, the loss of orthogonality is not bounded by order epsilon kappa x, but order epsilon kappa x squared. And this was proved by Jalbi and Philippe in 1991. All right, so in this plot, we have matrices of various condition numbers, and we're plotting the loss of orthogonality, all right, in the 2 norm, right, with the dashed line here plotting epsilon, MATLAB's epsilon kappa x and epsilon kappa x squared. And so clearly, BMGS with MGS is not bounded. It violates this bound here. Okay, and so the matrices that we've used here are the Leuschli matrices, and we'll use these again throughout the talk. And these come from a 1961 work by Peter Leuschli. And this matrix is a well-known test example used for various applications, including orthogonalization, since they're subject to a high rate of cancellation. Okay, and Jalbi and Philippe also proved in the same paper that if you instead use reorthogonalized modified Gram-Schmidt as the intra-ortho, then this block variant does in fact behave like MGS. Right? So it satisfies this order epsilon kappa x loss of orthogonality. Okay, so going back to that quote we saw on the previous slide, it's clear that it does actually matter in some cases what we use as the intra-ortho, depending on the block orthogonalization scheme that we're using. Right? Certainly you could lose something by using block MGS and then continuing with MGS. Okay, and so there are 2 questions, two things we can think about when we're talking about block Gram-Schmidt variants. Right, so the first is if I use an intra-block orthogonalization routine, a muscle with order epsilon loss of orthogonality and an order epsilon relative residual, what's the best a skeleton can do? Right, what's the best a block Gram-Schmidt orthogonalization can do? And then on the other hand, if I'm given some skeleton, right, some block Gram-Schmidt variant, what are the minimum requirements on the intra-block orthogonalization scheme or the muscle such that I get a good loss of orthogonality, or at least what I would expect from the non-block variant. And I will say that all the plots I'll show today are generated using this BlockStab MATLAB package that was authored by Catherine Lund, and you can find on her GitHub here. And this implements all the algorithms you'll see here today. And our code has simple drivers that you can run either block algorithms or non-block algorithms, and you can easily extend this to implement your own if you wanted. And so for each plot I'll show you today, I'll give you the exact MATLAB command used to generate that plot at the bottom so that you can reproduce them and play with them if you want. Okay, so an outline of the rest of the talk. So I'll give a brief overview of muscles, right, or the non-block methods, mainly because I'll need the stability results there when we talk about the block methods. And then I'll look at BCGS-based skeletons and BMGS-based skeletons. And then we'll end with a few open questions. Okay, so first, we'll review the muscles. All right, so in 1974, Kielbashinsky proved that for CGS, the loss of orthogonality has this quite loose, but still valid bound, right? So this S here is the number of columns in my matrix. And so it's a very weak bound. It's rare in practice that CGS would behave anywhere close to that badly. All right, and in 2005, Giraud, Langu, Rozlozhnik, and Van den Eschoff wrote a paper that says, as long as order epsilon kappa squared x is less than 1, then this bound is not, to the s minus 1, it's just kappa squared. And then a year later, Smoktunovic, Barlow, and Langu published a paper that clarified that the result in this result that was published before actually only holds if you compute the diagonal entries of the R factor in a special way, using a Koleski-like formula via the Pythagorean theorem. And they call this method CGSP for Pythagorean. And so the main idea is this, right? In a step of CGS, I update the above diagonal entries of R using Q transpose X. And then I compute the new orthogonal but not yet normalized vector W, right, by subtracting out Q times R. And so if I denote the norm of X as phi, right, and the norm of the above diagonal entries of R as phi, then for CGS, you compute the diagonal entry of R as the norm of W, which is really just computing the square root of phi squared minus c squared. Okay, whereas for the Pythagorean variant, instead, you do everything else the same, but you compute the norm of W using this formula, right? So the diagonal entries of R are computed as they are in the Koleski factorization of the normal equations matrix. And the key point is that if you use this formula, you can't guarantee a relative Koleski residual of order epsilon, whereas you can if you use this formula. And that turns out to make the difference. Okay, so it's very common to use CGS with reorthogonalization. And this is just one round of reorthogonalization. And this is often called the twice is enough principle, which comes from Parlet's book, The Symmetric Eigenvalue Problem, in which he attributes it to Kahan. And this is interpreted to say that an iterative Gram-Schmidt process on two vectors with one step of reorthogonalization produces two vectors orthonormal up to machine precision, as long as my matrix is not too ill conditioned. And in his 2008 paper, Stewart points out that this is actually frequently misunderstood, and Kahan was talking about speaking in the context of orthogonalizing a Krylov sequence. And what he meant is that either the vector is already almost fully orthogonal to the current Krylov subspace, or the norm of the vector is so small that I pretty much already have an invariant subspace. Okay, and so there was work in the early 2000s that extended the twice is enough idea to more than two vectors, basically showing that orthogonalizing twice is enough to get order epsilon loss of orthogonality, no matter how many vectors you have. Right, and there's also previous work on this by Abdulmalek. And so there are many variants you can, many variants you can construct. Right, so I can just run CGS twice, I can do inner reorthogonalization, or I can do some kind of selective orthogonalization. All right, and something I'll cover a lot in this talk are the recent developments in developing low synchronization variants. And there's a low synchronization version of reorthogonalized CGS in this recent work by Shrirovich and others in 2020. And so the motivation there is reducing the cost. Right, so if I use just reorthogonalized CGS, I can have up to 4 synchronizations per column, and they reorganize things to get it down to 1. All right, so this is the algorithm, and it looks very scary, but let me just point out the main ideas here. And so the main idea is that I have this associated orthogonal projector. Okay, and this T here, this T matrix, I can write this as I minus L transpose. Right, and so the idea is this T gets split into two parts that are applied across 2 iterations. So first, you'll compute a strictly lower triangular matrix L 1 row at a time using just a single reduction, and that'll contain all the inner products you need for the current iteration. And the second main idea is to delay the reorthogonalization and normalization. Okay, and so this is an idea that has also the idea of lagging things in this way as also appeared earlier. And so the effect is that reorthogonalization happens on the fly. And I won't go into detail here, but I would refer you to this paper. And so here's a summary of what is known about CGS variants, right? So I'll show tables of this form quite frequently. So I have the bound on the loss of orthogonality, right? The assumption on the condition number of the matrix under which these bounds hold, and then relevant references. And so one method I didn't talk about, but I'll comment on briefly, is this method of Stewart, which is CGS with selective reorthogonalization and replacement, where the key idea here is that I'm going to replace low quality vectors with random ones. And this allows you to handle rank deficient matrices, even matrices with 0 columns. But the trade-off is that in the worst case, it could be as expensive as householder QR. Okay, so this is a lot of this low sync version, it's conjectured in the paper that there's order epsilon loss of orthogonality, but no proof yet. Okay, and so now we'll talk about MGS, and in particular, I'll focus on details of the low synchronization variants, since we'll talk about those more in the block case later. And so the low synchronization variants that we'll call them were developed independently by Barlow and Schwieridowicz, although it's not clear that these authors were aware of the equivalence with Barlow's work in 2019. Right? So we can take a different couple perspectives here. So in one case, you can think of this approach as reducing synchronization by merging inner products and doing this batching and lagging. Right. The other perspective is that I want to cushion my projector with what we'll call an error sponge, right, to get CGS-like communication, but with MGS-like stability. Right. So here's my projector for CGS, for MGS. Right, and the idea here is now I have something that's kind of the form of CGS, but I'm going to stick something in here that will make it behave better. Okay, and this is a table of the existing variants categorized based on what form of error sponge they use, so T transpose or T inverse transpose, and how many synchronizations there are. So these are 2 synchronization versions and 1 synchronization. And so the fact that the product of elementary matrices for the householder QR factorization can be represented as a compact WY matrix was originally derived by Schreiber and Van Loon. And this together with the Sheffield observation, which makes the connection between householder and modified Gram-Schmidt QR factorizations were really the basis for Barlow's derivation of his algorithm, which he calls MGS2, but we're going to call MGS SVL for Schreiber and Van Loon. And Puglisi introduced an inverse compact WI representation for householder transformations with a lower triangular matrix D. And he noted that updates that would then use lower triangular solves. So this is where the LTS comes for. It's for a lower triangular solve, right? And the lower triangular form of the compact WI representation for MGS was developed by Bjork. And so the difference between using matrix multiply or triangular solve seems to be minimal in the experiments we've tried. Right? There seems to be an order epsilon difference there. And likewise, there seems to be an order epsilon difference between these two. Right? But going from 2 synchronization to 1 synchronization, at least in the block case, you will lose something, and we'll see that later. Okay, and the crucial point will be that these algorithms return not only Q and R, but also T, right? So they return this error sponge that they've created, and this can then be used by a block algorithm. All right, so here's a summary of modified Gram-Schmidt variants. All right, so the bound on MGS SVL were proved by Barlow in his 2019 paper, but for these other low sync variants, stability analysis remains open. Right, but there are some conjectures existing. And I also want to point out that while MGS SVL, the bounds here look the same like MGS in terms of loss of orthogonality, there's something special about it, namely that it outputs this T matrix, right, as do these other variants. And that's what will allow it to work well as an intra-ortho for the block generalizations of these. And so there are also reorthogonalized versions of MGS, but I don't think there's a real reason to use those in practice, since you do just as well using CGS with reorthogonalization, and that would be preferable from a performance standpoint. And I'll also briefly mention that there are other muscles that can be used that are non-Gram-Schmidt based. Some interesting ones are Koleski QR, so with 1 synchronization, 2 synchronizations, and 3 synchronizations. All right, so I've heard it said that thrice is enough for Koleski. And this is competitive with TSQR, which can be seen as a single reduction with QR factorization as the operator. Okay, so at this point, maybe I'll, before we get into the block variants, I'll stop and ask if there are any questions so far.
Hey, Erin, this is Julien, and hi. And I would like, what is CGS I plus and MGS I plus?
Right. So the I plus is maybe what you'd be more familiar with. It means, I'm for each inner loop I'm running it twice. So I run that inner loop and then I run that inner loop immediately again. whereas just the plus without the I means I just run the method and then I take the output and run orthogonalization on that method again. So it's a subtle difference. Does that make sense?
Yeah, at least Julian is not speaking anymore, so I guess it makes
sense.
Well, Bart, are there any questions on YouTube?
No, there are no questions on YouTube.
Okay, then let's go ahead.
Okay, great. Okay, so now we have what we need to talk about the block Gram-Schmidt algorithms, and we'll start with block CGS. Okay, and so here's the BCGS algorithm, and believe it or not, there's no existing proof on the loss of orthogonality for this block CGS, at least not that I have been able to find. So maybe someone can correct me on that. But I think it's a pretty safe conjecture to make that you can prove the same bound as you have for CGS, right? Because I mean, really, how much worse could this really be? So again, this bound is very weak, and in most experiments, this is not indicative of what you'd expect to see. So maybe there's a better bound, and I'm actually not sure whether you can construct a problem which attains this bound for BCGS or CGS. If someone knows, I'd be interested to hear that. Okay, so here's just an example that uses what in this paper from 2006 are called glued matrices. And so again, I'm plotting the loss of orthogonality versus condition number for BCGS with household or QR. All right, and so again, I have order epsilon kappa x and kappa x squared. And so the main point here is that it's very clear from this example that like CGS, BCGS cannot be order epsilon kappa squared x, right? And so I won't call anyone out, but it's often stated incorrectly that CGS and BGS have order epsilon kappa squared loss of orthogonality in the literature. And this is a simple counterexample that proves that. And I'll say for CGS, at least this is true if we don't use the Pythagorean base variance. Okay, and so just like there was a way to fix CGS using the Pythagorean theorem, we ask whether there's an analogous fix in the block case, right? In other words, I want to make BCGS better at Koleski. And it turns out that there is, right? And so here's how we do that in block CGS. Right, so let's just look at, here's the BCGS over here, just tiny in the corner. So if we just take lines 4 and 5, where I compute my new block W that's orthogonal to the other blocks, and then I call intra-ortho to orthogonalize the columns within W. And so that's how I would usually get the diagonal block of R. Okay, so if I take this equation and rearrange it, I can write X is QR plus W. And then I'm going to define QR factors of this above diagonal blocks of the big block R matrix and of my original block column X. So I have two QR factorizations here, so the R factors are P and T. Okay, and then so taking this QR factorization, I can write here T transpose T is X transpose X. And then from the fact that W and this QR here are orthogonal, I can get this next line, right? So if I take this transpose itself, so I have X transpose X is W transpose W plus this R transpose this R. All right, and then using the fact that the block diagonal piece of R is the R factor of W, and P is the R factor of the off diagonal R blocks here, then I get this equivalent expression. All right, and so this can be manipulated, and if I rearrange things, that means that this block diagonal of R, right, this K plus 1 block, can be written as the Koleski factor of this matrix, okay, or of this matrix. And thus that gives me two different ways of defining a Pythagorean variant of block CGS, right? One that uses this expression, right, which I'll call PIP for Pythagorean inner product, and this one that uses this expression, which we call PIO for Pythagorean intra-orthogonalization. And so we can modify BCGS to get either of those two versions, which are typeset here, and I've just highlighted where this new way of computing the diagonal blocks of R. And in addition to these papers, an equivalent algorithm was derived by Yamazaki and others here, and they actually derive an algorithm equivalent to BCGS PIP as a preliminary step toward the block generalization of the low sync variance. And their motivation in that paper was reducing synchronization cost, in particular within S-step and pipeline Krylov methods. Okay, and so in this work, which has been posted as a preprint, we prove bounds on the residual and loss of orthogonality for these new p variants, right? And the result is this. So assuming that your matrix condition number is not more than 1 over the square root of the machine precision, and if your intra-ortho satisfies this bound on the Koleski residual, okay, and this bound on the residual, all right, then if you use either the PIP or the PIO variants, this will give you order epsilon kappa squared loss of orthogonality and an epsilon order epsilon relative residual. And I'll note that these are pretty loose constraints on the intra-ortho here. Pretty much anything you would want to use satisfies these, including CGS, MGS, Koleski, etc. Okay, so this is the same plot I showed before using the glued matrices, where we saw that BCGS, violates this bound, right? But we see here for the p variance it doesn't, right? At least until we've reached 1 over the square root of epsilon. All right, and I'm also I'm using CGS and house QR here, and you can see that in this case the intra-ortho doesn't really make much of a difference. You wouldn't gain anything, for instance, by using BCGS with reorthogonalized CGS as the intra-ortho, right? So this, the point is that even with an incredibly stable muscle here, BCGS itself is sketchy as a skeleton. Okay, and so there are reorthogonalized variants, just like in the non-block case. And so the key work here is a 2013 paper by Barlows and Smoktunovich, where they prove something about reorthogonalized BCGS. All right, where this is their R-type step version of their algorithm. So you have 2 BCGS steps and then you combine them. All right, so they proved if you do this, as long as you have an intra-ortho with order epsilon loss of orthogonality, and your condition number is bounded by 1 over epsilon, then reorthogonalized block CGS will also give you order epsilon loss of orthogonality. And their approach, I'll go over a bit of their approach. Their approach is to first prove bounds on a sub-problem, right, which is given a near left orthogonal matrix U and a matrix B, I want to find S, upper triangular R sub B, and a left orthogonal Q such that this holds. And this subproblem is present in every step of the algorithm as long as the previous step has given you something that's near left orthogonal. And so in the analysis they use in this work, they require a bound on the size of these quantities coming from the subproblems. And so their analysis works inductively. And if we look back at the requirements on the intra-ortho here, it's clear that we need this constraint in order to guarantee that the first U in the subproblem, which is Q1, is near left orthogonal, right? So that you satisfy the base case of the induction. And so indeed that turns out to be the case. So here I'm using again the Leuschli matrices, and I'm plotting loss of orthogonality for reorthogonalized BCGS with both householder MGS and CGS as the intra-orthos. And so you can see that yes, this happens. You don't get BCGS reorthogonalized, doesn't give you order epsilon loss of orthogonality if you're using anything besides householder in this instance, right? Because these don't satisfy, the Q1 you produce is might not necessarily be near left orthogonal, and then things can go wrong, right? So this constraint on the intra-ortho that it has order epsilon loss of orthogonality matters, at least for these matrices. Okay, so but we can play a trick here. And so remember that the constraint on the loss of orthogonality in the intra-ortho was really just so we satisfied the base case, right? So what happens if we try to use a less stable intra-ortho like modified Gram-Schmidt, but just do one reorthogonalization, just reorthogonalize the first block, right? Then what happens? And if you do that for MGS or CGS, it does seem to work out fine, right? At least for this example, right? So here this BCGS I plus 1 means BCGS I plus, but with just reorthogonalization on the first block, right? So I'm using MGS or CGS twice on the first block, but then just use regular non-reorthogonalized from the second block onward. All right, and that's an interesting result. I would presume that you could also use some kind of hybrid intra-ortho routine where you use householder QR for the first block and then CGS after that, right? But that's something I haven't tried. Okay, and just like there was a low sync version of CGS with reorthogonalization, there's also a block generalization that's possible. And so the algorithm looks maybe even scarier in the block case. But an interesting, and I'll refer you to this paper for detail where you could find an equivalent thing as figure 3. An interesting thing is notice that there's no intra-ortho call here, okay? And this is our typeset version from our survey paper. It doesn't necessarily show off the merge synchronizations, but there's the communication patterns are made more clear in this paper. All right, and so as you recall, it was conjectured that the low sync variant of reorthogonalized CGS was order epsilon in loss of orthogonality. So the question is, what can we say about the block variant? And that's really an open question so far. And so this is a plot that does a good job summarizing block CGS variants. Right. So again, I'm plotting condition number versus the loss of orthogonality. And here I'm using what are called monomial matrices, where each block is computed as a monomial basis with a random starting vector. And so I'm using both CGS and householder QR as the intra-orthos, right, for block CGS, all right, the Pythagorean variant of BCGS. Then this is reorthogonalized BCGS, and then reorthogonalized BCGS with just reorthogonalization on the extra reorthogonalization on the first intra-ortho call. And then here's this low sync variant of reorthogonalized block CGS. Okay, and so right, so this does a good job of summarizing things. So here, BCGS violates this bound regardless of what intra-ortho we're using, as we know it can. Right, whereas for the block variants, they remain under epsilon kappa squared x, but only they stop working at some point after we've reached 1 over the square root of the machine precision. Okay, so if I use a stable intra-ortho, something with order epsilon loss of orthogonality, then we know that reorthogonalized block CGS will work. And we've also seen experimentally we haven't proved anything, but if you use this +1 variant, you could use something less stable like CGS. Okay, and so then the low sync variant, it's clearly not order epsilon loss of orthogonality, but it's something, right? Okay, and so here we have a summary of all the BCGS variants we've seen. And again, this entry here, this plus RPL is Stewart's block generalization of his CGS with reorthogonalization and replacement. And that has, will work no matter what matrix we give it. All right, so one thing to note here is that the BCGSI plus bounds require that the intra-ortho has order epsilon loss of orthogonality, where we conjecture that in the +1 case, it might not. Right? In our experiment, it worked even with CGS, but again, we haven't proven anything. I think it's doable. All right, and based on our experiments, I will conjecture that this low sync reorthogonalized BCGS actually can be as bad as order epsilon kappa squared. Right? It didn't look so bad here, but I have examples where it's order epsilon kappa squared if you want to see them later. Okay, and I'm not sure about the assumption on kappa x. I don't know. This is an open thing. Okay, and so now with the time left, we'll finish up with block modified Gram-Schmidt. And so we already saw earlier the classic results of Jalbi and Philippe. And so their intuition for the behavior of block MGS was this. Right? Here's block MGS, and if I look at lines 4 through 8 and rearrange them, I can see that my W is computed by a projection that looks like this. And so each of these projectors individually looks very similar to a step of CGS. And so they conclude that this indicates that there's some CGS-like nature to block MGS. And to repeat their results here, they proved that block MGS with MGS behaves, as they say, like CGS, although the bounds are actually better, I suppose. But if we use block MGS with MGS, reorthogonalized MGS, then we get something that behaves like MGS. And actually, you can manipulate the proof in their paper to show that this will hold for any, this better bound will hold for any intra-ortho with order epsilon loss of orthogonality, not just reorthogonalized MGS. And so that means, for instance, that block MGS with householder QR, TSQR, reorthogonalized CGS will all behave like MGS, that is having a loss of orthogonality bounded by order epsilon kappa x. Okay, and so what about the low sync variants? And so here's the same table of non-block low sync variants that we saw before, just to remind you. And it's relatively straightforward to generalize these all to block variants. And so in Barlows' 2019 paper, he has BMGS SVL with MGS SVL as the intra-ortho, which he calls MGS3. And he also has the block version of MGS SVL with householder QR, and he calls this BMGSH. And so in our recent survey, we include block generalizations of these other variants, and block generalizations for the one sync case were also derived by Yamazaki and others independently. And so in terms of stability, the only bounds that exist here are the ones that have been proved by Barlow. In particular, nothing's really known about nothing's proved about the one sync variants. Okay, so I'll take a minute to go through Barlow's analysis, the key points, mainly because I think that similar techniques might be used to prove something about the lower triangular solve version. Right, and so in Barlow's analysis centers on three quantities, right? So the T matrix here is the block variant of the error sponge, right? And S here is a quantity defined to be the upper triangular part of Q transpose Q for the computed Qs. And in exact arithmetic, this would be the inverse of T. And so this delta TS basically bounds how far away T and S are to being inverses. Delta QR is the usual residual, and we also have this gamma, which is I minus T times the computed R. And Barlow shows that as long as the intra-ortho satisfies these bounds, right, where the S and T, the non-calligraphic S and T here are the non-block equivalents of the S and T before, then the block variant satisfies these equivalent bounds. Okay, and then Barlow also shows that these things together imply that the loss of orthogonality will be bounded by order epsilon kappa x, as long as this constraint on condition number is met. And also in this paper, his 2019 paper, Barlow directly proves that MGS SVL does satisfy these constraints on the intra-ortho. Okay, so you might ask, okay, what can I say about using the block variant, this block T variant, if I use an intra-ortho that doesn't produce any T itself, it doesn't give me any error sponge. And so in this case, you can just see these as implicitly producing T is equal to I, right? So in this case, the bound, this delta TS for the intra-ortho can be bounded by just the loss of orthogonality, right? The residual stays the same, this is the usual residual, and actually in this case, the gamma becomes 0. And so what this means is for these non-T variant intra-orthos, if you want to use those inside a BMGS SVL, you would need to have a loss of orthogonality bounded by order epsilon, right? If you want it to behave like MGS. And so you could use householder QR, which again was used by Barlow, but you could also use reorthogonalized CGS or TSQR. And so you might ask the question, okay, can I mix and match these T variants, right? Could I take BMGS SVL with MGS LTS as the intra-ortho? Okay, and sometimes that works, but the answer is generally no, right? The behavior is it is not the same in general. Okay, and again, we can see this good using our good old Leuschli matrix. Right, so here I have BMGS SVL as the skeleton, right, composed with all the 4 different low sync MGS-based intra-orthos. And the only one that obeys this order epsilon kappa x bound is BMGS SVL with MGS SVL. Right? The other ones don't work as well. Right, so there's something about the compatibility of error sponges that has to be worked out. Okay, and again, I am using the Leuschli matrices, and I'm comparing BMGS, MGS SVL, and the one sync equivalent of that, which is called BMGS CWI for compact WI. Right, and I'm using both MGS and householder QR for each of those as intra-orthos. And so one thing, there's a lot to unpack here. One thing to point out is that while it seems like the loss of orthogonality for the non-block one sync versions is order epsilon kappa x, the same is not true for the one sync block variants. Right? So it appears that these are these one sync versions all go above order epsilon kappa x. Right? So you lose something going from 2 sync to 1 sync. Right? So BMGS CWY doesn't have loss of orthogonality bounded by epsilon kappa x, and further it stops working at some point, like once you reach about 1 over square root of epsilon. And so this is an effect of the skeleton rather than the intra-ortho, because it really behaves the same whether I use MGS or householder QR. And so I don't know what's happening, but again, I suspect that the norm lagging might be the culprit. And another thing to point out is that BMGS SVL really does need either MGS SVL or an intra-ortho with order epsilon loss of orthogonality. Right? If I try, so I'm just looking at the orange line with the X's, if I try to use BMGS SVL with MGS, it doesn't work very well. It's just as bad as BMGS MGS, right? Which is expected since I'm I'm not producing any T matrix here. Okay, and so here's the summary of what we know about block modified Gram-Schmidt variants, right? So for BMGS, we get a different bound on loss of orthogonality sometimes depending on how good our intra-ortho is, right? And this was proved by Jalbi and Philippe. And for BMGS SVL and the LTS version, you need either order epsilon loss orthogonality, or you need to use your specialized corresponding intra-ortho that gives you your error sponge that you can use. Although for the LTS version, it's just our conjecture. This hasn't been proven. And for the one sync versions, the CWY and the ICWY, it doesn't appear to make a difference in any test that we have tried what you use as the intra-ortho. Right? Both CGS and householder QR behave the same in some cases. And in either case, you get an order epsilon, a loss of orthogonality bounded by order epsilon kappa squared x in the worst case. And further, it only seems to work as long as this constraint is met. So order epsilon kappa squared is less than 1, which seems to be due to the Koleski factorizations that are used within that. And so in any case, the fact that the loss of orthogonality is not order epsilon kappa x means that I don't expect that you could prove that an S-step GMRES or block GMRES method that uses those is backward stable. Will it work sometimes? Yes. Will it, maybe it'll be faster and work most of the time, but I don't think that you could prove backward stability using that. But something to be investigated. Okay, so to sum up, right, so the Gram-Schmidt process, been around a long time, but is still very much alive. And there's been really a flurry of recent work on this, coming up with new variants and seeing how much we can squeeze performance and stability out of them. And there's also still a huge number of open problems to be solved. We saw a lot of conjectures today, so there's still a lot to prove. One thing I didn't mention here today is the possibility of randomized Gram-Schmidt algorithms. And there's been some recent work on that by Balabanov and Grigori. And also, I didn't talk about the opportunities for mixed precision approaches, which is currently, I'd say, a hot topic. And there was work about 6 years ago now by Yamazaki and others that uses a mixed precision Koleski QR factorization within block CGS and block MGS. And there's also been some recent work on using mixed precision in householder QR factorization. And so we still have the bigger questions of why we started looking at all this stuff in the first place, of determining what are the necessary and sufficient conditions on the degree of orthogonality that you need in order to have a backward stable block or communication avoiding GMRES method. And so the guess is that it's order epsilon times the condition number of some augmented matrix that involves the block Krylov basis, since that's like what you have in MGS GMRES, which we know is backward stable. But there's still a lot more work to do in that area and more to uncover. And so there really wasn't time for me today to talk to you about all the cool things about block Gram-Schmidt variants. So if you want more, I will direct you to these links where you can find the preprints of our survey paper and the proof for the block CGS Pythagorean variants, and also the BlockStab MATLAB package that you can play around with in your free time. Okay, and again, you can find these slides anytime on my website here. And so thank you very much for your attention, and I'm happy to take any questions or comments.
Thank you, Erin, for the very nice talk. There's one question on Zoom so far by Valeria, and I just let Valeria speak up.
Hi, Erin. Thank you for your talk. And I have a question about block GMRES. And people have been struggling with the deflation strategies because the block will lose rank at some point, actually very soon. In fact, people have implemented also sequential versions, like in block QMR. So what do you say in this respect?
Sorry, what was the question?
So what do you think? I mean, would this be easy to implement, because this breaks up the within block orthogonality issue, because you have to eliminate some of the columns and the number of columns changes. How does it work?
Yeah, that's a good question. How using such a thing would play into everything we know about the block orthogonalization. That's a hard question, I think, but it's something that should be looked at for sure. Yeah, I think that's a super hard question.
Okay, thank you.
Okay, at the moment there's no further question on Zoom, so I will ask a question. You mentioned this in the conclusions, but maybe could you elaborate a bit? Are all these variants, do they make sense in the context of Arnoldi methods, or are some variants just don't make so much sense?
Right. So I conjecture that you need something that's at least like modified Gram-Schmidt for a Krylov method to work. This kind of says, I'm losing orthogonality somewhat at the same rate as my residual is decreasing, and somehow that is still okay. And so, yeah, some of these variants that don't satisfy that order epsilon kappa x, I would say I'm not sure if could they be useful? Yes. Can you prove backward stability of a Krylov method that uses them? I don't know. I don't think so, but we'll see.
Okay, thank you. I will move to Bart for YouTube.
There are two questions on YouTube. One is of Gérard Meurant, and he's asking of the good methods, which one is the fastest, in sequential or in parallel?
Right. So of the good methods, well, which ones are the good methods? I don't know. I would say that I would say the low synchronization versions that do two synchronizations are maybe the most promising from the trade-off of performance and stability. I think you could get better performance if you go to the one sync variants. But let me see if I can find my. Yes, here's an example where I'm using. Well, this is for the low sync version of CGS, but let me see if I have one for the. I thought I put it in here. Right. Okay. So here I'm using the one sync version, and no matter whether I use CGS or Householder QR, they all don't satisfy this order epsilon kappa x. So going from two sync to one sync, there is a cost, and I guess depending on your application, whether the trade-off with loss of orthogonality is okay for you or not will make the difference. But I think that the two sync versions that Barlow worked on are a good, maybe the best trade-off.
Okay, thanks. Then there's another question, maybe you understand it better, but somebody asks, Robert or Robert, can you please also show the other results for BCGSI plus LS?
Yeah, well, maybe, so I hinted that I had something bad to show, and maybe that was this one.
Yes, okay.
Right? So here, these are the Leuschli matrices, and again, this is a great test problem for these and the glued matrices. If you really want to push your orthogonalization scheme to the limit, and I'll note that sometimes if you have a nice matrix, you don't observe such bad behavior. But if you do one of these kind of bad examples where here there's we're subject to a lot of cancellation, so things can go wrong. And so here I'm using the BCGS low sync version with reorthogonalization. And remember, there's no intra-ortho for this variant. And so that goes above, this seems to scale like order epsilon kappa squared. So I would conjecture that that's what it is, but I don't have any proof that it can, so I know it's not order epsilon kappa x, but whether it could be worse than kappa squared, I don't know. And you can see here that it's really, you don't gain, the reorthogonalization doesn't really gain you very much asymptotically versus just using, let's say, the p variants, non-reorthogonalized.
Okay, and then there's one last question. So this is all typical worst case error analysis, but can you say something about the more average error, let's say for random matrices or matrices that are sampled from interesting distributions?
Okay, so I don't have any, I can't say anything intelligent about matrices that are sampled from any distribution. But I can say that yes, a lot of these things are worst case bounds. For example, so a lot of times in practice, CGS will not. You will never see. Okay, I don't know. So maybe someone can tell me if you can see this kappa to the n-1 behavior from some canonically bad example, but I have never seen it. In fact, it does even without using the Pythagorean fix. It's usually, kappa x squared. And these, I will also note. Let's see if I have anything here. So I talked before about like, oh, you cannot mix and match these low sake variants. And here's an example where you can, right? So these are for these glued matrices. So they're bad for the Leuschli matrices, but for the glued matrices, they all seem to perform, just the same, right? So this, here they're order epsilon kappa x. These ones don't go, before we saw that only, MGS SVL with SGL works, but here you can seem to mix and match and they all do about the same. So although I cannot say anything for about anything intelligent about statistical stuff.
Okay, I think that's it for YouTube. Thanks, Erin.
Mm-hmm.
Okay, there's one more question by Cleve on Zoom, and I let him unmute. Hope this works. Cleve? Okay, now it worked.
Okay, now then. Okay, thanks, Erin.
Mm-hmm.
Sometimes round-off error analysis leads you to modify algorithms, tells you to change something. Does your analysis ever do that, or does it just verify things that you already knew worked okay from experiments?
Right. Well, one thing. Okay. Just the error. So one thing, and I don't know if Jesse's here and who's listening, but one thing that you can see by looking closer at the analysis was this BCGS I+1, where, okay, if I actually look at the analysis, this constraint on the intra-ortho, that it's order epsilon loss of orthogonality, is really only needed to satisfy the base case. And then the induction kind of takes care of the rest. So this kind of hints that like, okay, I'll use like I'll use something expensive for the first block. And then after that, I can use something cheap. And the block reorthogonalization takes care of the rest. That's what it seems to be. Also, I think that looking closer at some of these things, maybe it might hint at maybe some mixed precision approaches, right? Because we see like for a lot of these things, especially for the CGS variants, I would say it doesn't matter what you use as the intra-ortho in a lot of cases, right? Whether I use the CGS or household or QR, it seems to work the same in a lot of cases. And so maybe that hints that, okay, I could use something in lower precision and then it would still work. But I haven't tried that yet.
So my question is, which comes first, the analysis or the experiments?
Oh, I think it's an iterative process.
Yeah, I agree.
Yeah.
Okay. So twice is enough in that iterative process or not?
Maybe not always.
So there are no further questions on Zoom.
Okay. Yeah, then I think I'll just take over. Thanks a lot to Erin and to everybody who participated in the discussion. And now let me just, oops.
I stop.
Yeah, if you stop the screen share, I can pull my slide with the upcoming, it should be this one. Yes. Okay, good. I hope you can see it. Yeah, our seminar will continue in 2 weeks with Gunnar Martinsson, and then we will run until May 5th. And after May 5th, there will be, in the week after, I think there will be the SciM LA meeting. And that's, I think, for the Americans, the summer term. For us here, we will just have started with our spring semester or summer semester. But anyway, so we have made a plan until then, and then there will be the SciM LA. And afterwards, we'll see how we will continue. And good. So I hope we will see everybody in 2 weeks.